moment. Engineer Ganpati Reddy Garu, our treasurer, our Srinivasan Garu also on the dais, please. Now may I request our chief guest, Engineer Ganpati Reddy Garu, he is the engineer and chief ENC, R&D department. A very hearty welcome to you, sir. And the president, Vijay Sanabji. Bhimrao Garu, please occupy. The office bearers, please kindly be attentive. Less time your names. So when I call out, please occupy your chair on the dais. A special request from my end. As we all know, when we start anything auspicious, especially something that we need to do with knowledge, we start with the blessings of the Almighty. So I request all the dignitaries on the dais to please proceed for the lighting of the lamp. Light dispels the darkness and leads us towards knowledge. Request Mansa to kindly come over for the prayer song. All the press and our media personnel are requested to please occupy their space on the left side of the hall where a special place is created for them.
समस्तलोकशङ्करं निरस्तदैत्यकुञ्जरं दैत्यरोधरं वरं वैभवक्त्रमक्षरं रूपाकरं क्षमाकरं मुदाकरं यशस्करं मनस्करं नमस्करोमि भास्वरम् नमस्करोमि भास्वरम् नितान्तकान्तकान्तकान्तिमन्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्तकान्त కృంతనం నితాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాంతకాंతకాंతకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतకాंतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकांतकां നാരായണം ഹൃദന്തരീനിരന്തരം വസന്തമേവ യോഗിനാം തമേകദന്തമേവതം വിചിന്തയാമി സന്തതം ഹൃദന്തരേ നിരന്തരം വസന്തമേവ യോഗിനാം തമേകദന്തമേവതം വിചിന്തയാമി സന്തതം വിചിന്തയാമി സന്തതം.
Thank you, Mansa, for invoking the prayer. Now I request the Chairman, ACC Hyderabad Center, Shri Kashiram Garu, to please welcome the audience.
Good morning, all. Good morning, all. A warm welcome to you guys. Respected dignitaries on the dais, Chief Guest Ganapati Reddy Garu, ENC, President Vijay Sanap, our presiding today's NATCON, Sana President, Vice President Mr. Rajkumar Garu, South Vice President West Sandeep Shederkar Garu, Secretary General Vijay Vish Garu, Treasurer R. Srinivas Garu, Organizing Chairman Reddy Garu, our Center Secretary Garu, as well as our Dynamic Center Treasurer Ramesh Garu, and all our MC members. I welcome you all for today's the great event, NATCON, National Convention of Civil Engineers. I don't know how to express my gratitude to all of you, all the sponsors and all the delegates. Words are not coming to me because we never expect this much of gathering in Hyderabad. My heartful thanks to all your audience, all the delegates, all our fellow engineers, all the architects and builders and developers, and also all the sponsors for supporting us. I hope you will enjoy the 2 days technical sessions and interact with the speakers, and you take more and more knowledge for our construction industry. This unity shows the strength of our construction industry. My thankful to all of you. With this, I welcome you all for today's and tomorrow's the great event, NATCON, National Convention of Civil Engineers, Rising High. The caption is Rising High. Hyderabad is rising high with the tall buildings. That is the reason we have selected this caption on this topic also. Speakers are coming all over the globe. I request you all interact with the speakers also. Thank you very much. I welcome you all.
Thank you, Kashiram Garu. Now I would request the Secretary General, ACC India, Engineer T. Vijay Vishnu Maya, to please kindly address the gathering.
Presiding Officer, President of ACC Vijay Sanap, Chief Guest of today's function Ganapati Reddy sir, Vice Presidents, Chairman of Hyderabad dignitaries on the dais, and all the members of ACC family and the civil engineering fraternity. Ladies and gentlemen, first and foremost, let me compliment and appreciate the greatest effort put on by Hyderabad Center led by Kanchiram for the wonderful show over here. The magnanimity of the hall, the great exhibition of commitment, the presence of international level speakers and the delegates, it has not come in a 1 or 2 days. Association of Consulting Civil Engineers has toiled, worked hard since the last 38 years. Everything starts with an experience for falling down of a Gangaram building in Bangalore. Just evoked some thinking with the 7 great engineers from Bangalore to outlay something to reach out to the people of the civil engineering construction fraternity and assimilate knowledge of the construction practices and quality maintaining exercises, including the safety aspects of it. That's what we started. 7 great engineers. Very much fortunate to have 3 of them. So I would like to make the mention. They are is there. Umesh B. Rao, the founding member, the legendary people, Garudo Dwajan sir, Dr. Ram Prakash sir. Ladies and gentlemen, give them a very big round of applause. And all these 7,000 members who are now here, it's all because of the greatest thinking and commitment and honesty of all these people. These are the aims and which are there, but this is not the right time to talk about that. But ACC is going into a not only national level, but international level also. That this type of international seminars, it is being organized, shows the commitment and the teamwork attitude of all the 7,000 members. From the past 2 years, from the past 38 years, the history itself shows the performances, presence, and the commitment what we showed in the ground, and even the greatest seminars which is being conducted, that itself is the answer where our actions spoke much, much more than our words. Last 2 years has been one of the monumental one. 2,500, more than 2,500 members were added. 14 centers were added. Now we are in our target of going all over the pan-India. Now 39 centers are there, and these 2 years we are very much full, and we are sure in the coming 2 years we will cross 100, where ACC will one of the chief address of technical solution finding exercises. Different centers at all level are making their effort to make presence felt in the organization in the construction industry. And ladies and gentlemen, those who are not the members of ACC, please come and join us. And our next target is 10,000 members, 100 centers, and in the future days, we should be the #1 civil engineering organization of India, and definitely most acknowledgeable and most recognizable engineering fraternity institution of the international level. Hearty welcome to all the international delegates over here. Thank you very much for gracing this occasion and raising the standards and the value of this great NATCON. Compliments to everybody. Let us enjoy the 2 days of knowledge assimilation, acquiring the knowledge about the latest trends of civil engineering, where learning is a great process of everybody's successful life. Thank you very much.
Thank you so much, sir. Now I request President Sri Vijay Sanabji to his opening remarks.
Good morning. Today's chief guest ready. Here is on the dais. Founding members of the association, past presidents of the association, office bearers of various centers, and friends. This is the second edition of NATCON. First one was held in Mumbai last year. Hyderabad is taking the legacy further, and I'm sure that 2 days are going to make a lot of difference in your life as well as ACC's future. We have come here, we have gathered here, not only for the knowledge, but to meet each other, to network with each other, to explore the possibilities in the future. So I request you not only to be attentive throughout all the sessions, but let's get out of your comfort zone. Let's meet each other. Let's meet new people, network with them, talk to them. And I'm sure these next 2 days are going to make a lot of difference in everybody's life. There are really good speakers on various topics. I'm really thankful and congratulating the organizing team for having such a wonderful topics and such a wonderful speakers from across the world. My dear friends, organizing an event is not a small task. Shortlisting the speakers, talking to them, and especially when they are from abroad, organizing such events, so you just understand the pain behind the show and be attentive for next 2 days. Let's unlearn, learn, and relearn about the tall buildings. We are already late. I will not take much of your time. Thank you and wish you all the best.
Thank you, President Sir, for your opening remarks. It's time that we listen to our chief guest, Sri Ganpati Reddy Garu. He is Engineer-in-Chief of the Buildings Department, and the beautiful urban scape of Hyderabad city that you see today is all thanks to his continuous efforts. He's a perfectionist with an impeccable sense of the subject, and he ensures that all the work that is done perfectly. And that's how you see the ever-evolving urbanscape of Hyderabad coming up so beautifully that today, when we travel out of Hyderabad and we talk to people, they say, oh, Hyderabad, it looks like another Manhattan, or it looks like one more United States of America. That's the urbanscape we have today. And I think we should be really thankful for such Herculean efforts from Ganpati Reddy Garu and his team for this beautiful city that is ever evolving. So with these few words, sir, I would request you to kindly come and address the gathering. Ganpati Reddy, sir.
The president of this association, Mr. Vijay Sanap, Vice President Rajkumar, and other dignitaries on the dais, and other members of this very big association. Very good morning to all of you. I first of all congratulate the organizers for choosing Hyderabad as the venue for this two-day event. As you all know, Telangana in general and Hyderabad in particular is growing very fast, and particularly the spurt of high-rise building construction is visible in both private and government sector. After formation of Telangana state, you know, the construction in private sector is almost in an unprecedented manner it is growing in Hyderabad, and particularly high-rise buildings. Earlier, the buildings used to be around 9 floor, 10 floor maximum. Now 30, 40 floor buildings are coming in Hyderabad. So in government sector also, we are not far behind. We have been constructing the tall, very tall buildings. If you take some of the buildings we have constructed in the recent past, our police command control center is close to 300 feet tall. Our secretariat is 265 feet tall. Ambedkar statue is 175 feet tall. So like that, we are constructing very tall buildings in government sector as well. So when it comes to adopting the latest technologies, in government sector, we have constructed PEB buildings. Within 3-4 months, government wanted us to construct medical colleges for taking admission in government sector. So 9 medical colleges we have constructed in 4 to 5 months with PEB structures. So we also have constructed perhaps the largest stainless steel facade, Martyrs Memorial. It is almost more than double the size of Chicago bean. So in government sector also, we are adapting the latest technologies, and our Center for Dalit Studies, we have utilized all those composite structure elements in constructing that Center for Dalit Studies. And we are also adopting all the green features in our buildings. We got green certificates for our Police Command Control Center, for our Secretariat. Perhaps these are the first administrative buildings to get green certificate, gold rating by IGBC. And if you take the magnitude of the building construction we are taking in government sector, when Telangana was formed, as far as R&B department is concerned, we had about 30 lakh square feet buildings in government sector under R&B control, roads and buildings department control, both residential and office buildings put together. Today, in the last 9 years, we have added 1 crore 5 lakh SFT to the existing 30 lakh SFT buildings. So we have added more than 300% new buildings. And we are constructing another more than 1 crore buildings. They are under construction. And several buildings are particularly in hospital and medical education sector. We are constructing huge buildings. So given the background of development of high-rise buildings in both private sector and government sector, it is apt that this venue, this event is being organized in Hyderabad. I really thank them and congratulate them. And to take care of these safety issues in high-rise buildings, government also has constituted a committee for making amendments in the existing laws, municipal laws and safety laws, to give the best and safest buildings to the end users, whether it is in government sector or private sector. So government is equally interested in adopting all the latest technologies and going in hand with the private sector, with all the experts in the industry, and because of that, we have also sponsored some of our important officers who are associated with high-rise buildings to participate in this event, gain the knowledge, and for using in our buildings. So I wish all the organizers and the delegates to make use of the knowledge that is being imparted here and help in development of safe buildings in Hyderabad. And I wish you all the success. Thank you.
Thank you so much, sir, for your address and taking us through the compliances that are going to come and the progress that we intend to achieve. Now may I request Vice President South, Shri Rajkumar Kashara Garu, for his closing remarks of the inaugural session.
Good morning. It's a great morning and happy morning to all of us basically, because all of you are here. Respected Presiding Officer President Vijay and today's chief guest, Sri Ganapati Reddy Garu, Engineer Ganapati Reddy Garu, Engineer in Chief Buildings, Government of Telangana, and my colleague Principal Office Bearers, Sandeep, VP West, and the Secretary General Vijay and Treasurer Srinivasan, and the office bearers of the Hyderabad Center, Mr. Kashiram, Organizing Chairman Mahendra Reddy, and the Bhim Rao, and Ramesh Garu, and the founder members, and the speakers, invited speakers from all parts of the world. Thank you very much for coming, honoring our invitation and coming here. Thank you very much. Dear friends, it gives me immense pleasure to here be for the NATCON Hyderabad. Previous year it was in Bombay, and the theme of the future. This year the theme of the building tall and resilient, about the tall buildings. We shape our buildings, thereafter they shape us. How true this is as engineers who have the onus upon us to create sustainable, resilient and futuristic structures. The theme for this NATCON, building tall and resilient, rising high, touches upon the much needed issues of the growing population and need for the workspace, housing and various other utility spaces. Yet, retaining more of the natural ecosystem, our focus now shifts from the horizontal spread to vertical spread to address the need. Engineering is the moral studies of the intellectual life that continuously crusades to create more value to the quality of our human lives and ecosystem. With this pursuit, Association of Consulting Civil Engineers India chose to delve into this topic. I, as a part of this team, feel extremely privileged to have an enthusiastic team with a never say no attitude. I appreciate the Hyderabad Center team headed by Chairman Kashiram and the organizing Chairman Mahendra Reddy and all the torchbearers of this center and members of the working committee, all the members, really kudos to you all. You made it possible. And all of you, congratulate all of you, compliment all of you. Because of you, we are forced to close the registrations yesterday because we are overcrowded. Hall is full. Our capacity, our work capacity now. So that is because of all of you. You made it. Thank you very much for making it. And I thank all the international speakers who agreed to join us to share the knowledge, especially Darshan in a short notice coming, and all the speakers coming in a short notice. Majid, especially thank you for obliging today. And sir, Ganpati Reddy sir, I know how busy your schedule is. You made this landscape of Hyderabad with iconic structures we can reckon with. In Hyderabad, have you seen this Martyrs building, or Ambedkar statue? The name, your name will be in annals of the history of the Telangana, and definitely it will be reckoned permanently. And yes, sir, we should give a big clap to him. Command Control Center, 300 meters, 300 feet tall, because of his efforts and his team efforts, his team sitting here. Congratulate to all of them. And many such structures. Builders are there who are building now 40 floors, 53 floors in Hyderabad. This is apt for the Hyderabad. And I thank each and one of you for making from all the centers with different parts of the country joining for today's inaugural and the today's seminar. Let us take back home with a lot of expert speakers' learnings and make it as a grand success. Because of you, who made this as a grand success, let us learn and unlearn to be a great civil engineers. Thank you very much.
Thank you so much. Now may I request the organizing chairman, Engineer Mahendra Reddy Garu, to kindly propose the vote of thanks. Before that, I would like to invite our president and the chairman to kindly felicitate our chief guest, Shri Ganpati Reddy Garu. So please kindly accept a token of gratitude from Team ACC India and Team ACC Hyderabad. Request Chairman Kashiram Garu and Organizing Chairman Shri Mahendra Reddy Garu to kindly felicitate President Vijay Sanabji. Let not the energy of the hall go down. We need claps. Ladies and gentlemen, we are still in the first half of the morning, so energy has got to be high. Your claps are an encouragement to the people on the dais for their efforts. It's just a small thank you from our end when we clap. Next in line to be felicitated, our Vice President West, Sandeep Shirkedkarji, Team Hyderabad Center, kindly felicitated. Next in line would be our Vice President South, Shri Rajkumar Kasharla. No. Sufficient business. Our Secretary General, Shri Vishnu Vijay Mayaji. And the most important person for any organization, the Khajanchi, the Treasurer of ACC India, Shri R. Srinivasanji. Thank you for the felicitations, gentlemen. Now I request our organizing chairman, Engineer Mahinda Reddy Garu, to please propose the vote of thanks.
Good morning, dear respected chief guest, engineering chief R&B, Sri Ganapati Reddy Garu, ladies and gentlemen, distinguished office bearers of ACC headquarters, my team ACC Hyderabad, and all members of ACC and delegates. I stand before you today at this NATCON 2023 seminar on building tall and resilient with great pleasure and honor. On behalf of the organizing committee of Hyderabad chapter, I extend my heartfelt gratitude to each and every one of you. Grace us for your presence here in Hyderabad. This seminar would not be possible without the generous support of our sponsors and exhibitors. We are immensely grateful for their unwavering commitment to this event, which is contributing significantly towards its resounding success. I would also like to express our sincere appreciation to our themed speakers who have taken the time out of their busy schedule to share their invaluable knowledge with us. Their expertise and insight will undoubtedly enrich our understanding of building tall and resilient structures. I hope you find their presentations enlightening and inspiring. Once again, I extend my deepest gratitude to all of you for being a part of this remarkable gathering. Our aim is for this seminar to serve as a platform for networking, learning, and for forging meaningful connections. Together, let us explore new origins and pave the way for the future of tall and resilient structures. Thank you all once again for your presence and support. And thank to the Warangal and Rajahmundry Center giving the good number of registrations. Thank you.
Thank you so much. Now may I request all the dignitaries to kindly proceed for the inauguration of the exhibition, where we have lots of stalls, and all the audience, we can catch up with the exhibition during the lunch break. So please be seated because we will be starting the session shortly once the inauguration is done. Get the next speaker's presentation ready. Get the next speaker's presentation ready. The first speaker. Our first speaker for the day and the first session, the topic is Design and Construction Challenges in Tall Buildings. And the speaker is Mr. Majid Hashmi. He is the MD for KMH Engineering. So while Mr. Majid Hashmi aligns his presentation, I welcome Mr. Majid Hashmi to this August gathering today to share his knowledge. Mr. Majid's expertise is built on his 33 years of global experience, primarily in Dubai, where he has been responsible for the design of many tall and super tall buildings, many which are over 300 meters and few over 400 meters in height. He spent more than 20 years as the head of the structural design department with a famous consultant in Dubai, designed more than 200 tall buildings and 13 super tall buildings. One of his buildings, the Princess Tower, was in the Guinness Book of World Records from 2012 to 2015 with 107 floors, and it's known as the tallest residential building of the world. His passion is learning, knowledge sharing, social networking, running for marathons, and many more. He has delivered more than 30 keynote presentations, interactive lectures and seminars, conferences and summits throughout India. By education, he is an ME, that's Master of Engineering, Structures from Osmania University, professionally licensed engineer from the state of Maryland, United States of America, licensed for design of unlimited floors from Dubai Municipality. He's done a complete structural concept analysis and design of world's tallest residential building at Marina, Dubai, included in the Guinness Book of World Records, and he's a gold medalist from Osmania University for being the first in the Master of Engineering. So we welcome you, Mr. Majid Hashmi, and we look forward to listening to a very enriching session from you today. Thank you. Over to you.
Is it working? No, I will walk. Thanks for the nice words. Good morning. Good morning, everyone. Respected organizers, chairman, president, vice president, and secretary, especially Mr. Rajkumar for inviting me and for such a nice event organized in Hyderabad. Well, this being, all these dignitaries talked about networking, unity of all the team for construction of tall buildings, any type of construction, learning and sharing. So for this we are here, for sharing, learning, unity, networking, to understand each other. So this topic was given by the organizers, design and construction challenges of tall buildings. Challenges. But challenge is there everywhere in the life. And for the design, there are many challenges. I can't cover all the challenges. I will cover just few challenges on design and few challenges on construction. So what I thought is, the major thing is the beginning of the design. How to start and how to begin it. What is the starting point? So that is the concept design. So, concept design, all these design stages, we see on YouTube, but we don't practice really. We have practiced in Gulf and in West, US, Europe. But here in India, we are getting into it. So we have to understand what is the starting point of the design. That is the importance of concept design and initial investigations. All these things to get optimized design. So for getting the design optimized, we have to sit with all the teams from the day one. And because as you know, all the builders, they will come to you, come to consultants, and they want to start excavation directly on site in parallel to the design and drawings. So these are all challenges which we have to take care of in design as well as in construction. Well, the problem what I have seen in India, that engineers, architects, and VIP guys, they work in silos. Architects, he does the drawings, our good friends, and send it to email it to the structures, email it to the client, email it to the MEP, and they will design, they will put in model, and they will share the drawings. So this has to be, this will not lead to any proper design. We have to sit together, as our dignitary said, there should be a proper networking, sitting together and talking, come out of silos, improve your networking. So, let me proceed. What is concept design? Well, this is the starting point of the work. We have to get out of the room, please sit, understand the architecture, understand the client. We have to, again, see, I'm telling you, we have to keep our egos aside. Work parallel to the architects and clients, understand the site situation, constructability, availability, and the trends. And the trends of the local market. So understanding the architectural elements, we, structural engineers, we have to get into the architectural, understand the architectural, the high volumes, big double heights and everything. We have to respect the architects because they have lots of creativity. We do have creativity, but we have to go out and really think as an architect. In the same way, architects, they have to come in our shoes, think about the big spans, transfer structures, constructability, time, cost, all those things. So creating ideas on systems with approximate sizes and sketches. This is the concept stage. So sitting with architects, do some manual calculations, do some simple models, get some sizes, and that is the first point, the beginning point. And communicating themes, systems, ideas to client, architect and the construction teams. See, nowadays, see, any builder, any developer can come to you, I want structural steel. Tall buildings, why structural steel? See, we need to educate everyone. See, we need to learn, we need to educate everyone. Okay, what is the trend going on here? So we have to understand the trend and the systems available, the local availability and everything. See the trend. What is the tall building? So it's simple, just go to CTBUH, Council of Tall Buildings and Urban Habitat, CTBUH. There you can find all the classification. Tall building is any building which is less than 300 meters. And super tall building is a building which is from 300 to 600 meters. And mega tall are the buildings which are more than 600 meters. So there are only 3 mega tall buildings existing on board. The first is Burj Khalifa, Makkah Tower, and Shanghai Tower, I believe. And about super tall buildings, there are just 170 or 175 buildings, super tall buildings, from 300 meters to 600 meters. From 170 or 175, I have designed about 15 buildings, super tall buildings. So, in concept state, we have to sit together with our team, prepare the DPRs, sit with the clients, and the important thing is investigations. We have to install all the investigations, geotechnical investigations, the tests, we have to get all the onboards, like wind tunnel guys, and any seismic test if you want. Structural engineers, structural design to drive the design of tall buildings. See, for like expose, exhibition centers, no problem. Let us get this architectural sketch. Whatever the height, whatever the volume you want, we have to do it. We have to do it. But for tall buildings like 200, 300 meters tall, we really have to, the structural engineers have to drive the design. Come out of your silo, speak out, sit with architects, sit with the BB guys, sit with the clients, and explain them the systems, the trends, the availability, the local trends. And second thing, structural engineers to start work with architects from the day one of the pre-concept stage. Then with this, you will do some manual calculations, simple models, and you have to present to the client that what you are doing is right. Convince the architect that what you are doing is right. With some, I think CSI is here. Who is CSI? He has been Carlos Ott. You might have heard him, Carlos Ott. So, see this, there are lots of necks. And he wants only the core to come out of the podium for certain floors and then the floors. This is what he has proposed. Well, it's okay. He's architect. He can propose whatever he wants. But we have to talk. We have to convince him. Okay, this is the serviceability problem, constructability problem, and so on, so on. Then he has reduced this, okay, more necking and so and so, so and so, so and so. So what is the height? 330, 340 meters. And what are the dimensions? Just 30 meters by 30 meters? Just 30 meters by 30 meters. And it will stand for 340, 330 meters. And the core is just 17 meters. 15 to 17 meters. Just imagine what the ratio? 300 by 15? 20. So without doing any calculations, without doing any taps, without doing any hand calculations, just sitting in the office, I have refused. Mr. Carlos, it is very slender building. There are very few slender buildings in the world, including New York and Chicago, which have the ratios of 20. So 340 meters by 15 is more than 20. So sorry, I said, Carlos, please, you have to change this. I have explained him, okay, this is serviceability, constructability problem, time and cost, everything can be done. Yes, can be done. But not at this time. Because see, the slender buildings existing are in Chicago, which has a ratio of 20. It has so many dampers in it. Then this was the plan, 120 by 60, and he has some restrictions. He told me the building width cannot be more than 37, 38 meters. So I asked him to take the complete building, make it complete RCC. So these are the shapes, see, this is concept. He has given all these necks, but he has allowed me to take the columns up. You see the columns. So it is, he's getting his shape. I'm getting in my design. Yeah. So he's happy, I'm happy. How? I was not sitting in my office and he was not sitting in his office. We sat together in one common table, without calculations, without data, without AutoCAD. We talk, we discuss. This is concept. This is lacking. So we have to develop, these things, networking, sitting together, talking together. This is lacking. So option of structural steel at the top of people are cancelled. Architect has proposed exposed columns continued up and sky gardens there. So I was sitting with him, and my time in Hyderabad, They were playing with computers. It's all playing, it's all gaming. So never believe the outputs when any, your engineer he comes to your table with the outputs. You have to have some thumb rules, some basic calculations to check the serviceability and strength. Okay. So these are the systems what we have proposed immediately on this table. Flat slab, central core, the flat slab, and few columns in the periphery. He wants second option, okay. Any options? We have to give options because this is the concept stage. We have to be very flexible. We should not, force the architects and developers, working in their throats. No, you have to be flexible. You have to come up with multiple number of options. The second option, we have to composite sections because he wants to complete the building very quickly. With structural steel composite, we can do 2 slabs per week. So, to get more transparency, to see Burj Khalifa, he was trying to, minimize number of columns. So finally, see 4, 4, 4, 16 columns, and then again 16 columns, this way, this way. See, these are the concepts. How many options? The same, 2 or 3, this is the third day. I was sitting on this table. 4, 16 columns, 16 columns. Finally, just 8 columns and a core. 8 columns and just 8 columns and a core. 38 meters by 38 meters. Is it not a big floor plate? And see the offsets, all cantilevers. See, it's all by, this is concept. We have, the almost finalized, it was at the end of the concept stage, we had this shape, core. This core looks very thick, but it's not very thick. Core is system, and we have 4 systems, and all solid slabs, and we have peripheral beams only. It's all flat plate. So for MEP guys, friends, it is flexible to move your ducts and everything. In addition to core, we have outriggers. Central is the core. Outside we have columns. 4 columns here and 4 columns here. At few floors, at H/3 or 2H/3, we'll have deep outriggers. The depth may be about 4, 5, 6 meters. We connect with this, this blue, deep RCC elements to the core, to the outer columns. That gives tremendous amount of stiffness to the building. That control drifts. So this building was critical in wind because most of the tall buildings, especially slender buildings, usually they are critical in wind only. So these are the systems. Even for outrigger systems, it was not one. It was several outrigger systems. Some MEP floors, mechanical floors somewhere. So these are the default. We can give. So we have to be flexible with our MEP guys. We have to give openings because people want to go through the walls. They want to, for maintenance of equipments and so on. So these are the walls just shown to the architect. I asked them, okay, be happy. I will give all the cutouts, openings, windows, and pipes. You can pass through. So this is only conceptual space. I'm telling you conceptual space. Many types of outriggers and belts. You see the black one? These blacks. It is a combination of core, outrigger, and a belt, just to increase the stiffness, reduce the drifts. So we have very quickly studied, the behavior of the building, got the drifts, got the time periods. So within, it was the 4th or 5th day, my team here has done more than 25 sensitivity models. Sensitivity means you have designed the building. You should know what element is contributing what. If you remove this element, what will happen to the building? If you remove these 2 elements, what will happen to the building? That is the sensitivity study. So we have to study, and you are not doing it. You are young graduate. You have trained them. Just give me this. See, I was sitting there on his table, and I got more than 30 models on the end of the week. So getting all the sensitivities, what is the time period, how flexible it is, what are the drifts, and for wind loads, for earthquake loads, everything I had. Tall buildings in general, or super tall buildings, you can say, there will be following major effects of wind on tall building. Along wind forces, what we think, if there is tall building, this tall building will have wind in this way. So this will drift this way, right? That is the along wind force. But have you flied any kite sometimes? Kite will happen. So wind blows on the kite and sometimes kite moves this way. Have you noticed it? That is the across wind forces. Wind is following this way and the building is not moving this way, building is moving this way. Wind is this way and building is moving this way. That is crosswind forces. And third is wind buffeting. There are wind experts here, so I'm not going to talk more about wind. So this is only the things what I have learned from wind experts. These have been taken care. This all happening in concept stage only. We got this, I called, RWDI, have you heard? They are the pioneers of wind engineers, I called them. So we have discussed long. See the wind, the blue direction. That is the along wind. The green is the crosswind. And here see the shape of the building. You have to decide the shape of the building right from the day one. Okay? To reduce the winds. Lots of things. Double steps in the corners. This is called shape optimizations. We are not doing without any calculations. Just sitting on table, just calling wind experts, geotechnical experts, get their views, opinions. What they say? Double step corners. That will reduce wind, along wind on the building as well as to some extent across winds. Our building had also double step corners, hence reducing the along wind forces and cross wind forces. You have seen the building, it has double step corner. It's not square, it's not circle. It has step corners. Yeah. See, this is type E 101. It was beginning a square building. Because of this, there were lots of eddies, lots of crosswinds governing. What they have done, RWDI, they have proposed to give this double step corner shapes. And the double step corner should be at least like width by 3, or say width by 4, or width by 5, at least. So then your reduction will be significant. See, the corner configuration, UM and MC1. UM is without any corners and MC1. Say the forces drastically reduced down. And see FY. The forces came down by 2 to 3 times. What you have done? Nothing. No calculations, no models, nothing. You sat with the architect, you talked to RWDI, well, what to do? He said, no, just reduce these corners, get some corners, khadam, finish. So, see the forces reduced less than half. It's 1/3 the force. Yeah, same is my building. You see, this is the shape of the building. Double step corners, shape optimization. Learning, see, this is learning by talking, learning by sharing. And see, I repeat this. Share your knowledge and learn. Share, talk. Reducing along wind and across wind forces. There is one more thing. This I cannot talk. Wind specialists, they can't talk. Wake buffeting. You see, the voids. Architect has created some voids for the double height gardens, sky gardens, and so. See, these things, wake buffeting is the effect of neighboring buildings to my building. So, but luckily, this building, it's 340 and the business bay around Burj Khalifa, within 100, 200 meters, the buildings were of that 120, 130. Luckily, there was less wake buffeting here. So what RWD has asked me to shift these voids up to reduce the wake buffeting. But finally, it was not agreed, and this was not very important because the neighboring buildings were shorter. Wake buffeting. Yeah, other building. See, this is 2002 or 3, where Sheikh Mohammed had announced Burj Khalifa. And then everywhere, all over the world, people were coming. Developers were coming from India, from China, from Russia, from Azerbaijan, everywhere investing. They were, purchasing plot, paper, and coming to the consultant. I want to start excavation and sales. So, design and construction. So you have to design and you have to keep in mind all the construction things. And he wants very quickly. So this is Princess Tower, number 1. This was the world's tallest residential building of the world from 2012 to 2015. And it's covered in Guinness Book of World Records also. The height was 2,415 meters, 6 basements near the beach, and the ground was 100 floors. And the gravity system was only composite decking, just simple composite decking, and lateral load system was RCC frame tubes. And challenge was to cast 2 slabs per week. That's why we have opted for composite decking. And second, in the same building, similar floor plate, but we have gone for PT slabs, complete RCC, LLRS and gravity PT. Yeah, see this. If you get any plan from architects, they will give you some core and some plan. And they will say, okay, these are my driveways, these are my parkings, these are my flats, put your columns. What you will do? Ground floor. Where you will put columns? Apartments. What we do here, we follow the walls of apartments, right? But apartments are changing. Every 10 floors, every 20 floors, the apartments are shifting, the walls are shifting. What we do here in Hyderabad, I have seen everywhere transfer slabs, 1.5, 2 meters, I don't know. You waste 5, 10 crores, you waste your efforts, I don't know. Sit with architects, try to get rid of this. And one of my big developers here, he has, given me a chance, and the architect was listening to me. We got rid of all the transfer slabs. It was a fantastic building. I have covered it. See, these are architects. Go through it. You can have columns. But finally, and the client was asking for the flexibility because based on the sales, he can change the internal layouts of the blocks. Okay, fine. Then what I have done is just taken columns, closely spaced RCC columns, forming a peripheral RCC tube. So the system is LLRS, lateral load resisting system, is RCC tube in tube. This system was developed and implemented by an Indian, Fazlur Rahman Khan. He is an Indian, he is not Bengali, because he born in 1929. It was India, it was not Bangladesh. Right? So I call him an Indian. So Indian has started this tube Indian concept, Sears Towers, lots of towers in Chicago, New York. So, and the gravity system was composite decking. Construction. Because the developer, you want parallel construction. You have to get out of your table. We have got, investigated, soil investigation done, started, right from the day when I'm telling you. We have asked them to do all the seismic tests on soil and shear wave velocities, primary wave velocities, and Osterberg cell test. See, again, geotechnical engineers. We don't talk to him. We don't go to office. Sit with them and talk to them why you are getting less bearing capacity, why you are getting less pile load capacity. The pile load, we have some pile load, but after doing this Osterberg cell test pile, this pile was tested for 4,500 tons. And the settlement was less than 6 millimeters. So we have taken a capacity of 3,500 and less than that, reduced. See the pile layout. For 100-story building, you can see the columns. Piles are concentrated under the core, and 4 piles under each column, or 1 pile under each column. So this is the economy, you will get once you sit with the geotechnical engineers, talk to them, share your views, and get the market trends, talk to the contractors. So this is how you get things. What is Osterberg cell test? Piles, see how you test piles, cantilage beams and static load test, you load blocks, 4,500 tons. How many blocks? Maybe from here to here, all blocks, how you load. So this cell is a hydraulic jack, the blue point, you see, is a hydraulic jack. It is inserted in the cage, buried in the pile, and all the tubes and strain gauges, everything coming down. See, I'm not a geotechnical engineer, so you can ask our geotechnical experts here. So it is inserted, buried, casted, pile casted. You see those? The blue one inserted. Then you load the pile after sitting, after 8 days or 14 days, whenever you get the desired strength, you get all the deflections, strains along the skin friction capacity, and bearing capacity, everything. Casting of raft. Again, see, structural engineer is not only sitting on the desk. Please go out and talk to the contractors, talk to the design mix again. See, people think that, by adding more cement, you'll get good strength. It's strong. Please don't do it. Always ask the contractors to reduce cement. Please reduce cement, reduce water. See what we have done. This is the pile cap. See the number of pumps here. More than 12 number of pumps. Cast at 8,000 meter cube one go. Imagine the amount of heat. What would have done? Cast the concrete, leave it. Top will be very cold. Inside the temperature reaching. When the temperature comes up, what time? After 36 hours, 40 hours, 44 hours, 50 hours, you don't know. Usually the maximum peak temperature of the concrete core reaches after around 40 or 36 hours. So that happens in the concrete. And the surface we are cooling. So the core temperature is going to 70, 72, 74. The top we are cooling. The top is say 30. The difference is 40. You are creating a differential temperature in the top. So what we have done? We have covered the surface of the raft with insulation boards to reduce the differential temperature. And again, I'm not concrete specialist, just talking what we have done. These are the decking systems, 3 floors, people, 3 different teams working on 3 different levels. The first, insert plates, beams, deck is the advantage of structural steel. The building was slender. It was 415 meters tall, and the width was 39 to 40 meters. So the ratio was exceeding 10. It was, crosswinds were governing here. So RWI, they have done the complete design of damper. This is the damper. This is the tank at the roof, 17 meters by 8 meters, 4 meters deep. And the water has to be filled up to 2 meters so that you allow the water to splash on the walls. They have monitored the frequency of the building, measured the frequency of the building, live on the floor for 1 week. They got some frequencies. We got some ETAPS frequencies, predicted frequencies, and measured frequencies. The difference was coming about 20-25%. How come? Then what I have done from the beginning, we asked the contractor to take the cube strengths and find out the E actually. So we have taken actually, not the totally, because concrete is already there. We want M70, we got M80, M90. So bigger. So we have used actually, and we have found the difference has gone down to 10, 8, 12%. The difference between the frequencies, measured frequencies, and the model frequency. Yeah. One more building. This is in Thane. This is the tallest residential building of Thane. See, everybody they want logo and Kapil Dev, he is the ambassador for this one. This was designed by somebody else. Excavation started. This was the architectural plan. See, what is the system? He got some plan from architects. An architect has done some columns here, black. He has done some blacks. And he has started working on it. He has started model and he started design, the given foundation, 2.5 meters and everything. So this shape, what is serviceability? What is the strength? He has not studied. See, where is the core? What is the lateral load system there? Just a few shear walls, few small cores. Then he called me and he asked me, Majid, this is the building approved by authorities, Thane authorities, and we want to add few 10 or 12 floors. I said, this is not working. This is not an efficient building. We have to improve this and we have to add the floors. So these are the stages, concepts, what we have developed with architect. Previous architect and structural engineers were fired. We got new ex-office contractors, architects, sit together. See, the first one, modify. Second modify. Third modification. See, we have now proper cores using the same floor plate. And he has increased the floor area because he got more FAR. See now, there was no re-entrant corners. Yeah, see these corners now. We got this three Indian corners. Why? Because this building was also slender, 250 meters tall, and the ratio was about 8. So I was expecting cross means mega one. So from the day one, we asked the architect to get this three corners. I think now get the point. We have corners three Indian. You can see this has reduced the wind. When I shared the model with RWDI, Suresh, he said, amazing. You have done an excellent job by providing all these things. The building is performing very well. The accelerations are very low. So we got very reasonable values. With this one, we got very excellent optimization from concrete and steel. See the developments. So this is how the concept design works. Sitting architects. See, the red, all the red is the lateral load resisting system. It is a core with extended blades and then flanges. So it is not only core. You see, at the corners I have some small flanges because those corners at the extreme fibers, I was getting some tension over there, so I have removed some columns. The blue column I have removed that. So to load it more and reduce the tension. And blue are the columns which take only the gravity loads. Red is the lateral load resisting. So simple system. With this one, the steel ratios, reinforcement consumption, all developers talk about consumption. And we give some values. And again, in the later stage, after construction, Nadia, you have given so and so. See, I'm telling you, this is the ratio. 11 kilogram per FT, previous consultant. It is reduced. Why? Because we have increased the efficiency of the cores, extended blades, stresses, everything came down, stiffness increased. The consumption reduced to 5 kilogram per FT. 75 floors. I'm telling you, 75 floors, we just 5 kilogram per FT. And all the slabs are flat slabs. Simple. Geotechnical engineers. Client had given me a soil report. He said, no, we have rock, and we have rock since about 4 or 5 meters we are getting granite rock. Then what is the bearing capacity? He said 220 or 200 something. A rock, how you can get to? So it is rock completely. We have done again here the footing load test. I think I have covered. No. So we have done it, Thane. So all the raft before it is designed 2.5 meters thick raft and everything, it is gone. It's just simple, you see, strip footings, 1.5, 2 meters maximum, only a few corners, very nominal steep. So this is how, the concept design here is talking helps, networking helps, talking to geotechnical engineers, going to the sites, doing something. Just sitting in your office, working in silos is a disaster. This is in Hyderabad. 3 towers, 53 floors, what 200 meters tall, very experienced and expert in design. This is an advantage to me. He understands structure, he understands architects, he knows things. So you enjoy working with such clients. So he knows things. And whatever I say, Majid, what you have said is we will do it. We will do it. And see, this for high prime, high-end flats, 9,000 SFT, one flat, and that flat is about 7,000 SFT. And he wants all free spaces, big spans, and so on. So this was architectural. I told him, no, we have to drive the design because this is the construction critical, spans are critical, get the architect, so architect also flexible, Majid, what we have to do. We sat at the table and we have started all the systems and everything, fix the systems, architecture. See, I'm telling you, within 2 weeks, we have taken a good shape. This was a system. See, all flat slabs. We have few banded teams because of big spans and big cantilevers. See, this is the system. And no transfer slab. And we have 4 parkings below. So why we don't have transfer slab here? Most of the building you go and see, he will transfer slabs. Why? Because architect, he don't want to talk about structures. He will plan different parkings. He will put some columns. He will put different columns, at typical floors and put transfer slabs. Easy for him and expensive for the client. So see, such system, all the columns, complete system is going from foundation to roof. This has, given tremendous amount of savings in concrete steel. Loaded for 750 tons per meter square. The bearing capacity what he has given was only 200 tons per meter square. We have loaded, tested the rock at the foundation. No? Yeah. Huh? Okay. I will. So, I hope you're enjoying. You have energy? So, thanks. Last 5 minutes, I think we slide. Okay. So, elastic settlement was just less than 1 millimeter, around 1 millimeter. So, loading was 750 tons per meter square. Nothing is 100 per meter square bearing capacity. Minimum. 500. So, I got my specialist from Bombay. He came here, he has given budget, take 500 tons per meter square. So, getting proper people, having networking right from the day one again will help you a lot. That is all concept design. 500, tremendous amount of confidence has been saved. We have questions here? Again? Questions? Okay. So this was a building again designed by somebody else in North India. I don't know the name. It was, see the floor. Where is the core? Where is the column? Architect again has given the drawing to him. He has put the columns and he has seen there is no core, no proper core. It is not working. No proper core. Nothing. And they have started construction. That was casted and everything. And he has so many beams. It was just 45 floors. So many beams inside. The contractor was, banging his head. So he got some Dubai-based contractor, KCC, a American construction company. They came to me, they know me very well. Well, Majid, I want flat plate. Remove all the beams. We have removed all the beams, remove many columns. You see? These green walls we have removed. I don't want. Why I want the wall near the shear wall, near the core wall? See, we want to load the core wall. See, he is giving the core wall and again giving a column also. So how you will load the core wall? So these green walls we have removed. You see? Core is the proper core now. There are slabs resting on the core. Core is properly loaded. And it's a flat plate. Previously it was 200 millimeter thick slab, top and bottom mesh. Here I have given just one mesh, 125 to 150, only two thicknesses. Only one mesh, no top mesh. We have only extra top at the supports. So again, there was about 40% saving in concrete and reinforcement. Yeah, done. Questions? Thank you. Thanks.
Thank you, Mr. Majid, for a wonderful and insightful session. We request you to please stay on the dais, please. Now I request President Shri Vijay Sanamji and the Chairman ACC Hyderabad Center to come on to the dais to felicitate our speaker for the day. We also have
amazing words. आपके words हैं ना, आप दोनों के words मैंने याद. See, the networking is lacking, and talking and networking and everything.
we can take questions after the felicitation. And in case there are many more questions, we have a tea break right now. We can take it up in the tea break. We're just trying to see that there is no paucity of time for the other speakers.
Thank you.
Any questions from the audience, please? I see one hand go up. Can somebody from the team reach out to this gentleman?
Majid bhai, it was a wonderful talk.
Yeah.
Why a structure, all the donkey work for a building, for all the donkey work for the building, it's done by us. Why we are paid less?
We have to
A
be
structural engineer paid less.
We have to be positive. It was not donkey work. You have to enjoy your work. I'm telling you, going out of your table, going to site, talking to guys, you take it positive way and talking to architects, doing things. If you enjoy your work, you will get good outputs. So we have to take it in a positive way. It was a good question. I like it.
Any more questions for our speaker? Okay. I'll take that as the last question for this day. Oh, we have one more.
I'll come to you.
I think you raised a very good point that you had to keep everybody together, including the geotechnical engineer, right from day one. I wish you convey that message to all the structural engineers. I find that particularly here, geotechnical, not only here all over, geotechnical engineers are being treated like service rather than part of the design. You can save a lot as you did, and which I think is what I would like to support. Well done. Thank you.
Yeah. Very valid point, sir. See, we have to get the geotechnical engineers and we have to respect geotechnical engineers because he can save crores to you. Crores. Yes. I can hear.
Thank you, Majid bhai. So, Dr. M.R. Madhav, I interacted with the 40-story building. So, I took his advice. Actually, Dr. Madhav, he gave a very good suggestion. So, he helped me to reduce the excavation as well as the concrete thickness also.
Yeah.
And very well explained about the core, whatever you have done. So, we are trying to implement it also. Thank you.
Yeah. And further, in addition to the raft, whatever you do, you don't model your raft only in your model. It's wrong. You have to put your structure also there. You know, the stiffness of the structure will reduce your bending moment in your raft.
Exactly. What we have done is completely
with a
complete structure.
Yeah. Excellent.
Thank you.
Thanks.
Okay, thank you, Mr. Hashmi, and thank you, audience, for bearing with us. And I think this one, I'll take this as the last question, sir. And let's not have any interactions. Please post questions now. If there is any personal interaction, we take it during the tea break. Please go ahead.
Hello, sir. This is Ram Kumar.
Yeah.
What is the contribution of flat slabs to the lateral stiffness in high-rise structures?
Yeah, this is a problem. Contribution of stiffness. See, if you go to 13.920, the first, the first clause, number one introduction, it says, structural engineers has to decide and judicially the lateral load system. What is the system? Core and shear walls. Core and shear walls, your system, whatever you have assumed, should be capable of resisting full lateral loads, the code says. So if your system is core, means your core should resist 100%. Otherwise, if you see the computer, core is taking just 50%. Where the moment going? It's going with slabs and beams and everything. Core says, okay, crack the slab at 0.5 or 0.55. But still, the loads are going to the flat slab. If you are using flat slab system as a system, then there are very few buildings where the flat slab system has taken contribution of flat slabs is taken into account. It's really not good to use the contribution of flat slabs to lateral loads. Let us put all the loads to the system, core walls, shear walls, well systems, frame, outriggers, and others. Try to avoid.
Thank you.
So thank you. Please join us for the tea break. We will all come back to the hall by 11:45. It's 11:30 now, so 15 minutes of break. The next topic of presentation would be efficiency of tall building structural systems. So let's not get late for this important topic. Please come back by 11:45. Thank you. Is the next presentation ready? Request everyone to please come back to the hall. We are starting the next presentation. Request everyone to please come back. Request everyone to please kindly join in. In case we delay, we will be delayed for the day. Please cooperate. Our next speaker is going to be Dr. Naveed Anwar. He's the Vice President for Knowledge Transfer, Asian Institute of Technology. Can I request somebody in the exhibition area to help others to get inside the hall, please? Whosoever is still not finished with their tea, kindly get your teacups to the hall. You can enjoy your tea while listening to the session. So, our next topic is efficiency of tall buildings, structural systems, which will be presented to us by Dr. Naveed Anwar. He is currently the Vice President for Knowledge Transfer of Asian Institute of Technology, Thailand. Dr. Anwar is also affiliated faculty in Structural Engineering, Field of School of Engineering and Technology, AIT. He's got a vast experience of 35 years and has a unique opportunity to work in a very broad spectrum of the civil and structural engineering knowledge cycle. He's been invited as a keynote speaker in various international conferences. He has authored over 100 publications, including books, conferences, papers, journal papers, magazine articles, and reports. He's also been the key presenter, resource person in over 100 capacity building seminars, workshops, training programs conducted in more than 10 countries and attended by thousands of engineers in collaboration with several academic and professional institutions. He's worked on many innovative and challenging projects like wind tunnel test for structural wind loads of 40 meters high, Buddha statue at Thailand, wind tunnel test for structural wind loads of 81 meters diameter, semi-elliptical globe, Thailand, structural performance-based evaluation of 71 stories, grammar-free residence in Philippines, structural system review, development and detailed design of 37 stories, Central Embassy Park Building, Bangkok, Thailand. You can see he's got a vast experience in, I think, the wind tunnel test, and he'll be able to guide us to a versatile knowledge of the topic that he's going to talk to us about. So all of you who's not joining into the hall, I think we are starting with the presentation.
or increase efficiency by increasing but also at the same time reducing the cost. But cost-effective design would be that we lower the cost without changing the performance. And high-performance design would be that we keep the cost constant and increase the performance. And highly innovative design, which is very hard to do, would be that the cost is brought down and performance is increased. And that's what we are talking about a little bit today. How can we work on both ends of this equation, increase performance, at the same time reduce cost? So in that case, efficiency will go much higher. So with this concept, let's go into the details. Now for tall building structure, the efficiency will be measured in many ways: strength, stability, stiffness, ductility, redundancy, durability, constructability, flexibility, sustainability, and so on. Even aesthetics. So all of that has to be considered when we are looking at efficient structure. So let's look at structural systems. What are the possibilities that we have that we can choose from and how we can make them efficient? Typically, you must see this diagram in many books, in many references, many places. These are the sort of a menu of structural systems that you can pick and choose or have been in other buildings of various heights. And they range from all kinds of combination of structural systems. And if you just look at tubular systems, you will also see a lot of variation in very high, in very many buildings. But what I want to mention here is that we are not focusing on these kinds of buildings at the moment. We are focusing a certain type of range of buildings. I think Marshall, who was supposed to present in the morning, would have talked about these tall buildings. But what we are going to talk about is the buildings which are in the range of one buildings in tall building range. In fact, about 80% buildings, 75% buildings would fall in this range. Remaining are either smaller than that, and a very few super tall buildings, maybe in numbers, 10, 20, and mega tall maybe 10 less than 10. So most of the time, structural engineers would be involved in designing buildings which range between 150 to around 250 or 300 meters. And that is the about 50, 60-story building range. So our discussion will focus on this range. So let's look at the structural system of such buildings now. Now, what are we looking for when we say efficiency? As I mentioned, we are looking at several KPIs for these structures to measure. Because if you're going to do the measurement, we must have KPIs. And those KPIs are stability, strength, deformation, drift, ductility, energy dissipation, and motion perception. These are some of the more important of the KPIs for a typical building. And in fact, if I have to pick one, which is probably the most important, that would be drift. The interstory, true interstory shear drift, not the drift caused by deformation. And most of them are affected by nature period and high load effects. And we will also talk a little bit about that, how we can fine-tune nature frequencies on nature period and also reduce or manage the high load effects inherent in tall building design. People have come up with what they call 4 commandments for tall building design. That means 4 basic rules that if we follow those basic rules, we are likely to come up with a reasonably efficient or good structural system. So what are those rules? Number 1 is that vertical elements space far from the center. It's quite, all of these rules are actually common sense. There's nothing intricate or difficult about it. But once we follow them, they are likely to result in a good system. So obviously, we are looking at the vertical elements space far from the center of gravity. So we have the most lever arm, so to speak, to resist the lateral loads. Second, we should channel the gravity loads to those vertical elements resisting these overturning forces, which means avoid interior columns. So if we can avoid the interior columns, then we can take a lot of gravity load outside these exterior columns. And if you look at the tall buildings, many tall buildings, and you will find that the interior columns are often avoided. Or transfer loads are used to carry those interior columns and then transfer them to outside and then start again. So every 10 floor, 15 floor, transfer floor, or 20 floors, transfer girders will be used. And those columns, intermediate columns will be transferred to the outside column. Especially structures which are designed for the mega columns. So that is the second, I would say, guideline or commandment. The third one would be to link those vertical elements together with shear resisting large size elements which experience minimum shear drag. And this brings us to the concept of outriggers and all of that, and we will discuss a lot about that. So that's the third part. That first we have those columns which are par, and then we connect them together with the board and also with each other. And then resist the greater loads primarily with those members which are under compression due to the gravity load, which is, like I said, is an common sense. But if you explicitly apply them one by one, you will realize that they will result in a basic efficient system from start, and then we can refine it and fine-tune it. Now, to increase efficiency, we need to use engineering to beat the math, so to speak. That means if the math says 1 + 1 is equal to 2, efficiency or engineering or ingenuity or innovation would say that no, I would like to make 1 + 1 greater than 2. And that's where the efficiency of the structural system would lie. How can we increase, combine things together in such a way that with the same material or the same material, we get much more benefit? And one such configuration that we see is that if you have two shear walls, one column and one shear wall, or a group of shear walls, and if we can connect them together in a proper manner, then the combined stiffness of this system would be 8 rather than 2, which would be individual, individual stiffness added together. In this case, we beat the math by combining two things with this each stiffness of 1, and the resulting stiffness equal to roughly 8 or 7 or 5 or something like that. So this is what we are looking for in a tall building, that we combine these structural systems in such a manner that we get high efficiency in terms of stiffness, in terms of the nation period, and so on. So this leads us to the most important concept in tall building design, which is the outrigger concept. So the outrigger concept and similar members, they basically convert the bending moments on the building to axial forces in the columns, tension and compression, and hopefully just compression. And this concept we can take forward in any number of ways to add efficiency to this structural system. This will reduce the outriggers, will reduce a lot of things. They will reduce the tension period, reduce the displacement, reduce wave, reduce moment in shear wall, and they basically have to follow all of the board amendments, but they do not reduce shear wall. That's one thing that you cannot pull by adding the outriggers. So shear wall shear, the shear wall primary design, that will not be affected by the use of the outriggers. So the problem with outrigger is that they need space to be put in, and often the architectural plans may not give us that freedom that we can put in the outriggers where we want or where it's structurally most efficient. So that's why the concept of the virtual outrigger has become also interesting. So we have real outriggers, which are real members connecting the core wall to the outer columns, for example. But sometimes that may not be possible because it blocks the flow within the building, and architects may not allow you to block the floor unless there is a machine floor or something like that. So in that case, we can move these walls on the boundary, and they still act as outrigger due to the box effect of the floor, in which the floors act as diaphragms, and we can use that to stiffen the floor just as if the outriggers were connected to the shear walls. And this also leads us to the concept of the bell. So we get the benefit of outriggers, virtual outrigger and bells at the same time by putting these members on the periphery of the structure. Of course, they will block the windows, and then there are ways and means to provide openings in them. But conceptually, we could have virtual outriggers and bells into one system. So here you can see that the blue line on the blue structure above is a outrigger, but with the opening, so that weakens it, but at the same time, there are ways to handle those upping beams going into the shear wall. And the second one is the bell, which we have truss, which in which case can provide openings on the periphery of the structure. So there are a number of ways that this can be managed. But in any case, the combination of outriggers and bells is the key way that we can make these structural systems efficient for later floors. And this is how it can be used. So you can see a real outrigger, which is connecting the core wall to the columns. And then there's a virtual outrigger, which is connecting only the columns outside. And there's a bell, which is connecting the columns all around. So these bells work serve as an outrigger in one direction and bell in the other direction. And the purpose of the bell is basically to distribute the loads more uniformly on the columns that are supporting that. So it works very well. So this concept of outrigger bell, virtual outrigger bell is a very good one. And the second question is, where should the outrigger be located? Along the height of the building, and many studies have been done, many publications are available, which will tell us where the best location of the outrigger typically will be around 2/3 of the height from the base, but it will depend on the structural configuration. But what is important to see is that the outrigger places the top is not going to be so efficient. Outrigger close to the base will not be efficient. It will be somewhere in the middle because of several reasons. First of all, this will, if you put the outrigger close to the top, it will induce axial compression and tension into columns over a longer height, which will reduce axial shortening, which will reduce the stiffness of the column that are supporting it. So the effectiveness will be reduced. And also the length of the shear wall in between becomes long. So you can see here from the axial force diagram, shear force diagram, and information that if you place the outrigger somewhere in the middle third, it will have more effectiveness. The second important aspect in providing outrigger is that if you provide outrigger, it adds stiffness, but it doesn't add ductility unless we explicitly manage it. So ductility, as you know, is extremely important for tall buildings, especially this range in seismic prone zones. So we need to have a lot of ductility added to the buildings, and then normally the ductility will come from the shear walls, the base, using shear walls closer to the base or closer to the top of the podiums. And secondly, it will come from coupling beams, which are the connection between the shear wall components, or sometimes between columns and the shear walls. And also, we could add the extrinsic buckling restraining bases or dampers, which are also outriggers. So BRB serves as a very efficient member which serves two purposes. It becomes a kind of a brace. BRBs, we can actually add both stiffness control and ductility control to the structures. This is a typical BRB. We don't have a lot of time today to talk about that, but I'm sure you're familiar how the BRB works. But they're extremely efficient member and they are now being used. Initially, they were only used in low-rise buildings. But now, because the size of the larger BRBs are available, they are being used in tall buildings also. And these are two tall buildings in which AIT was involved, and these BRBs are used there. As you can see, at two different levels in both of these buildings. And they use several floor height, and they connect the outer columns to the core, and they act as outriggers as well as dampers and ductility devices. The other type of object that they can use to control which could have a similar effect as the outrigger, but not truly, are the flag or the floating walls. Because many times the outriggers cannot connect directly fully to the core wall because of the need for openings around the core. So by simply converting some of the partition walls into flag walls, you can then add this functionality or this efficiency into the tall buildings, because the partition walls are simply replaced by concrete walls. So the cost impact is less, the space utilization impact is less. This is, for example, usage in some of the buildings that we studied. In fact, this is one of the research at AIT, where the use of flag walls at different levels and different configurations was studied. And there is another study of using flag walls to create a kind of outriggers. Now, the next important aspect is that it's not only that we have to manage the design to provide for the forces that we get and try to economize or minimize the reinforcement or optimizing cross-section. We also can actually work on reduction of the demand or managing the demand itself. That will be forces, especially from earthquake and rain, both can be managed by proper structural design. So these are not something that are given, but rather can be managed by the structural properties. And so one of the key problem in tall building is that we have three key force types: the gravity, wind, and earthquake. And they all tend to demand different properties of the structure. So if you try to optimize or try to make efficient, one of the members, some of the members efficient for one, it might make their use inefficient for the other. And the question, mostly the problem is that if you, for example, designing the shear walls for wind and you provide a lot of reinforcement to resist the wind moment, that reinforcement will become a problem when you go to resist earthquakes because the durability of the walls will be reduced. And so this kind of, and a lot of times the buckling or connecting, not buckling, but coupling beams that are designed for wind may actually not work well for earthquake and so on. So we always have challenges between designing for these three different types of roads. And one of the key reasons is that wind load is a force generated load. That means there's a real wind which is creating a force both along and across. On the other hand, the seismic force or seismic force is generated by the structure itself in response to the motion. So it's a motion, a movement, motion-related force. And this is where we have the opportunity to reduce the force by managing the displacement capacity or the displacement patterns of the structure. But the problem is that some elements are fixed because of the wind and you can't go below them in seismic, so that makes the seismic design inefficient. So that is a big challenge for both the regions in which we have a high wind and high seismic demand, but also for regions in which we have a low wind and low seismic demand, because we don't get ductility or the yielding in the seismic forces that the code expects, like if R factor of 3, 4, 5, you can't get it because the seismic demand is not high enough, and wind is holding some of the design of the element. Second problem is that the design for wind and design for earthquake are almost opposite. One is based on elastic and one is more based on inelastic. So where wind design stops, the seismic design begins. So this also creates difficulty in managing the two together. It's not a load combination issue that you can pick higher of the two combinations. It's more than that, because they belong in different ranges of post deformation curve, and because of the nonlinearity inherent in seismic design, they can't be added together. So this really creates a lot of difficulty. And this R factor that you see in many codes, similar response protection factors, they are actually one of the biggest challenges. And I think Spennon in his presentation today or tomorrow will be talking a lot about that. So I will skip that here for the details. But this is an area where if you spend enough time, we can actually create efficiency in the system by looking closely at the wind response and seismic response and their design and reinforcement and so on. I think we cannot emphasize enough the importance of the modal properties or the dynamic properties of the structure, because everything depends on the basic mode shapes and modal properties, the initial period and vibration modes, because they sum up to give us the total response. So doing a proper design to manage the modal response or dynamic response is the key to get into an efficient structural system. And this affects the response in a number of ways. First of all, it basically changes the demand, seismic demand, because the first mode also will be typically very long in a building. The higher mode will be short, and depending on the response spectrum of your region, it will produce different demands for different modes. And here you can see the comparison between the response spectrum in Manila, for example, and Bangkok, very different forms. So here, the higher modes, for example, the middle mode here, mode 2, will actually have the highest contribution in Bangkok, and the first mode will be, first mode, third mode will be less, whereas in Philippines, the third mode will be producing a large demand, even if its contribution is less. So we have to study the dynamic response, the modal properties, and its relationship to the response spectrum of that region. to get a really nicely balanced structure. Sometimes stiffening the structure might be helpful, sometimes it will be not helpful. And second part of that is the impact, the higher order effects on storage shares and on non-linearity and yielding and all. Once again, I think Mr. Penning is going to talk about that, and Engineer Ron will also talk about that. So I will skip that just to use the data of the areas which also impact the efficiency of the tall buildings. So when we are looking at the structural design, we should go into the details of the higher order effects, the dynamic response, and its relationship to wind and earthquake. And that's why using performance-based design becomes sometimes very helpful in creating an efficient structural system, because it explicitly helps us to evaluate performance at various demand levels, at various staging levels, with various configurations and so on. So once again, I think we have a presentation about our PBT later, but for tall building, especially in the areas where earthquake demand is high and the building is in the range of 200 or less meters, this will be very useful or very helpful. Now, how do you measure the efficiency? We have talked about that we can improve the efficiency, we can modify the efficiency, but the question is, what are the indicators, what are the measures that we can use for measuring the efficiency? These are the global measures, and I think Engineer Majid, I just heard last part of the presentation, he was talking about the concrete volume and reinforcement volume ratios. That means how much reinforcement is used per cubic meter, per square meter, per meter length, and so on. And this is a good indicator as the final outcome of the structure. But like I mentioned, this is not only an indicator, because if we minimize this one and we increase the construction time or fabrication time, or we affect the long-term performance of the building, then that indicator alone may not be sufficient to tell us more about the structural efficiency. The other things are structural area per floor area, how much area is used by shear walls and columns and so on, and then the individual reinforcement ratio for various types of members like columns, beams, and so on, and then the demand capacity ratio. Both for utility and indicators, that technical indicators or engineering indicators that we would be evaluating. So these are some of the numbers that we got after we looked at the data from about 150 or 200 projects that AIG Solution and AIG has done in the past tall buildings, and we tried to see what is the most common number that you get. So in our case, the average number of floors was 58, that we do, the average height was 196, and so on. So we also look at the height over line ratio, min, max, and average. We look at the top floor area, average, and podium per floor, podium floor area per average. So we look at several averages for these real buildings to see what is the trend and what are the typical values that are used, both the extreme values and the mean values. And so this gives you an idea where a particular structure lies. Similarly, for beams and columns, you can look at the beam length per area, beam equipment thickness, beam volume ratio, column area ratio, column equipment thickness, column volume ratio, wall plus column ratio, and so on. So what will be interesting to see is this wall plus column area ratio, because that's the area that you have taken out of the floor from the usable, so to speak, and used for structure. This would be a good indicator to see how efficient our structure really is if we have taken this area. And it ranged from 2%, which is probably an extreme case, to 11%, but mostly around 5 to 6% would be a good ratio. We can get that. So this is the total area of section columns, structural columns, and shear walls divided by the floor area, and you get this number. So if you get something like that, it would look reasonable. Similarly, shear wall alone, you can see their contribution to this floor area, and then maximum thickness, minimum thickness. Once again, these are numbers drawn from real projects, so we can get some idea of the feel of the numbers that we get. Either are we close to the averages, are we too far, or does it make sense or not? So these are some of the indicators that we could be using to measure the efficiency of the structural system that we have selected. But the more important one probably is the efficiency of the utilization ratio and the event capacity ratio. So utilization ratio basically compares what is needed against what is provided. So for example, if you have 100 columns in a floor, or 50 columns in a floor, and most of them, the DC ratio is less than 0.5 or 0.3, that means you haven't really utilized the capacity of those members fully. And if you just one or two columns control that design and every other column is following that, then it means that the utilization ratio will be low. And we should be targeting a higher utilization ratio, especially considering climate change impacts, the sustainability, where every metric ton of concrete needs a lot of metric tons of carbon and so on. So we need to be aware that we use minimal concrete especially. So that's one way to look at the utilization ratio. And the demand capacity ratio could be one indicator of that. So the demand capacity ratio, depending on whether it is port control or deprivation control, we could have a range between 1.2, in some cases acceptable, up to 1.5 not acceptable, clearly more than 200 unacceptable. But when performance-based design, rules must be a little bit different. But if you're active and code-based design would be 1. Practical limit would be around 0.9 in code-based design. A good range would be 0.7. So if we are getting a demand capacity ratio of close to 0.7 in most of our members, we are likely going to have a good utilization ratio and an efficient system. And if it is less than 0.5, that means we are doing an uneconomical design. And this is once again the numbers from one of the building. So normally in AIT, when we do the building design, we always try to calculate the DC ratio ranges of a building. So we know how efficient or inefficient the design ultimately is. So this is, for example, for the columns. And we are looking at how many columns are below 0.5, how many columns are between 0.5 to 0.7, how many columns like this one. So in this particular building, you can see that 16% columns are less than 0.5, so they are not in a good range. But once again, if you try to change the column size, it might cost more in homework, it might not be architecturally acceptable, so sometimes that can be accepted. But we can still manage by using the appropriate concrete strength, by using appropriate reinforcement, so we can bring the DC ratio to about between 0.5 to 0.7 or between 0.7 and 0.1. So 0.5 to 1 in this particular structure is about 80% of the columns, which is a very good efficient design because most of the columns are being utilized well. So this is one of the exercise that we could do in our structures to see whether we ended up in an efficient design or not. Other evaluation parameters that we could also use are axial capacity ratio, building aspect ratio, bending rigidity ratio, carbon emission per unit area, perimeter enclosure factor, structural span line density, and so on. So there are many higher level evaluation parameters that have been developed for tall buildings, including architectural, sustainability, and even aesthetic, and the cladding, and many aspects. So these go beyond pure structural evaluation, so we can have parameters that can also be easily calculated and compared. So when we're comparing systems or comparing buildings, we could calculate these factors also and compare them. So, serviceability, like I mentioned, safety, economy, environmental, social, adaptability, everything can be somehow put in these factors or these parameters. Now, the last part of the talk would be on the efficiency of the optimization of the structural components. So, if you look at a typical building like this one, we have 4, 5, 6 components that have several types, and choosing the right type. For example, in this building, we can choose the floor, for example, to be reinforced concrete, post-tension concrete, or steel jack and concrete. Some of the examples. And we could choose flat slab, beam slab, and so on. In fact, these days, the tendency of most all buildings is to use post-tension flat slab and use the shear wall plus the combination of breakers, and then do a performance-based design to verify that the system works. Because in many codes, that will not be an allowed system in all buildings, because the flat slabs are not supposed to be part of the later load resisting system, as Engineer Majid also mentioned. So we need to make sure that they are excluded from that, but they still carry the gravity load well. So this is an efficient option to use. Steel jack and concrete also is a very good option. Reinforced concrete slab alone, not a very good option for all buildings, because the thickness will be high, it will be cumulative, foundation load will be large, and so on. So we should look for post-tension concrete slab and steel jack and concrete. For the beam options, we could have concrete beams. We could also have post-tension concrete. And post-tension concrete beams, actually, we may want to use because we are trying to eliminate the intermediate columns. So sometimes the distance between the core wall and the outer column may be 12 meters. And RC, pure only reinforced concrete beam may not be sufficient. So we may need to make it either composite or post-tension. So then we can span 12 meters, 40 or 10 to 12 meters by using this combination for the tall building, especially which have only the outer perimeter skin and then core. For the columns, we have more options, more variations. We have the reinforced concrete column, of course. We have steel column, we have composite columns of various types. We have composite I-section, we have composite, where the built-up shapes are used. These are used a lot in China and also in some other countries. Concrete filled tube is one of the most efficient concrete column that you can make. It has a high ductility, it is easy to form, doesn't require form work. The only problem is it has difficulty in action. But as a column, concrete filled tube would be probably one of the most efficient sections that you can think of. And then square concrete fill also could be used. So these are the various options that you can use for column. For shear walls, you can have a simple concrete, reinforced concrete shear wall, or you will also have now composite shear walls coming up quite popular, with where steel plates are used, or either the steel sections are used, or steel plates are used, or both. This is a new form of shear wall with steel plates on the outside and concrete on the inside that can be used in the US. And it has been successfully used in several tall buildings, and it seems to be an extremely efficient member because you don't require formwork for the core wall. And the formwork becomes the structural element, and you can minimize the thickness a lot. Construction is much faster, and it's just a very good system. So if you're looking for a very efficient core wall, then steel plates with concrete fill inside would be a very good one. Now, what are the things that we should be looking at when we're looking at the efficiency of these members? We are looking at curvature capacity or ductility, and we'll be looking at the moment capacity, two key indicators that we could look at. So both these indicators can be computed from cross-section analysis. So these are the plots of the PM diagram, for example, from the PMM surface. This is the plot of the axial force against curvature plot. And you can see here that the axial force, as it increases, the curvature capacity reduces drastically. So which means that if you want ductility in columns and walls, the axial load ratio should be kept to low 0.4, 0.5 or lower. Then you will get high ductility in both columns and walls. As the axial load ratio becomes larger, we lose a lot of ductility. So it's evident from these plots. And we also should be sensitive that the ductility is highly direction dependent. So a rectangular section, for example, would be highly ductile on primary two axes, but very unductile on the corner side. Because on the corner side, there is not enough, the concrete is not enough. and it will crash very quickly. So that's why the same column, which is quite ductile on the two primary direction bending, will not be so good when it's subjected to biaxial bending. And you can compare the capacity of same size columns. You can see here the column size is exactly the same, but the capacity would vary a lot depending upon which type we use here. Similarly, the ductility will vary a lot depending upon whether we use confinement, we don't use confinement, we use steel, we don't use steel. And same is true for shear wall. So by placing the reinforcement in shear wall properly, by confining it, we can actually enhance the efficiency of shear walls very quickly. By simply rearranging the rebars, not adding more. So if you move the rebars from middle to the edges, then we get a better capacity. And if you can combine that, we get better ductility. So here you can see, that if you confine the walls, you get very high ductility very quickly. So confining the end zone, providing reinforcement closer to the boundary zone, it will increase the efficiency of shear wall drastically. Now the last few questions, almost to the end of the presentation.
Yeah. Thank you so much, Sarah Ravid. It was a very, very enlightening session. Now I would open the floor for question and answers. We will take only 2 question and answers due to paucity of time. We will also share Professor Naveed's email address. Anybody who's got questions further can write back on the email and you will get back your answers. Quickly, we take the first question.
Good morning, sir. Considering the green building requirements, what would be the efficient or optimized structure? Is it RCC or structural steel or precast or composite? What is your suggestion?
Thank you so much. We all know that this is a major target in greenhouse gas emissions, and everybody is talking about this everywhere. Even the people who are not looking at it aware of this. Greenhouse gases. So would be targeted. So that's one of the
That's all, sir. Thank you.
Yeah, quickly, one more question, please. Okay, so since I don't see any hands going up, we would take it as no more questions. Okay.
Sir, only question is, which is the most economical design? Like how to come down to the which is the most economical structural design?
Procedure to use. We cannot jump to the conclusion for each project, each location, each construction methodology, each local areas, constraints. The answer will be different. One structure economical in one country, one region is not economical in another one. I can quickly give you an example. For example, these in UK, for example, they have a lot of structures using diagrade, which is very efficient economical structure using steel braces on the outside of the building. But that would not work in a region where you have high earthquakes. So if you bring that structure to an area with high earthquake, same structure which is very efficient, very economical, one becomes uneconomical. So it has to be locally evaluated, and we should evaluate them using proper scientific methods.
So thank you so much, Dr. Naveed. And now may I request Mr. Ong to please come on to the dais and accept a token of gratitude on behalf of Dr. Naveed. Request Rajkumar Kachakla to please kindly come and hand over the memento. Though it's an online session, I think an applause is definitely expected for the session. Whether online and offline, appreciation definitely reaches. Thank you so much, gentlemen.
Thank you so much. I'm really glad that we could share the knowledge, and I wish that I could participate in person next time. Thank you so much once again for inviting me for this event. Thank you.
Thank you so much. As we sponsor you is also a great initiative. So we have with us representatives from Ramco Siemens. Can we have them on the dais, please? A huge round of applause, ladies and gentlemen, to these people who have been ready there to sponsor and support ACC. And I request Rajkumar Kachakla and organizing chairman Mahendra Garu to please felicitate them. Okay, there's a commercial presentation. We'll just look at that.
A very good afternoon to everyone. I first of all like to thank organizers of NATCON at Hyderabad actually. So the topic is on tall buildings, rising high and resilient. So it is very suitable for Hyderabad. So which is on the path to be the skyscraper capital of India. So this is in the second place right now. So Ramco is very happy to be part of this NATCON and to be a part of your concrete also. Ramco Cement, we are a leading manufacturer of cement in South India. So we have a manufacturing capacity of 23 million tons. So usually when a greenhouse gas or CO2 emission is concerned, so the blame will be always on the cement manufacturer and steel manufacturer. So we have this thing in our mind. So sustainable growth is the main important thing which is required. So we had that vision 20 years back. So we launched our product Ramco Super Grade in the year 1998. So which is a Green Pro certified product. So we have this sustainability in our mind because of our ex-chairman, P.S. Ramasubramanian Rajagaru. So on his vision, so we have now launched the concept of right product for right application. So catering the needs of every category of customers. So we have every need for cement. For concrete, we have Ramco Supercrete. The similar way for plastering, we have Ramco Super Plaster. So we are addressing the requirement of every category of customer. For a precast unit, where the high strength is the requirement, we have Ramco Super Fast. So which will cater the higher strength requirement of the precast unit. So we created a winner. Yes, Ramco Supercrete is a clear winner because the growing construction phase, we need to address the strength requirement also. So PPC cement is we all know that PPC cement has a later strength gain. So we needed to address that issue. So we created Ramco Supercrete, which is a blended cement as well as has a cement strength equivalent to 53 grade cement. So it is crack resistant, so the repairing part will be eliminated. We also have this dry mix range of products where we manufacture tile adhesives, block adhesives. So as I said earlier, so Ramco Cement has it in its blood, the sustainability. So our Ramco Cement is the one and only cement company with the 4 Leaves Award for taking initiative in the latest technology, as well as our products are Green Pro certified. So this is a mines exhausted mine at Ramco Cement. So we have converted entirely into an ecological park. So 800 acres of mine has been completely restored and the ecosystem has been restored now. So this is located at Pandalgudi in Virudhunagar district. So keeping in mind, so to address the rising
structural system, and I would request Mr. Yeah, registration is going on. What more? I'm talking about that only. Why are we so quiet? So thank you. Thank you for the representative from Ramco Cements. And next we have our next sponsor from NATCON PT Structural System Private Limited, which will be represented by Kamala Kannan, Mr. Kamala Kannan, Managing Director. May we request you to please come onto the dais, please, and we have their presentation too.
A very warm good morning to all of you. Thanks to the organizer. I represent a company called NATCON PT Structural System, rebranded, and we are formally called as NATCON Structural System. We are a hardcore post-tensioning designer and execution in this country. Post-tensioning looks very, very interesting for these tall buildings because most of the tall buildings have become more sustainable and viable in construction if you adopt post-tensioning technique, because you have to do the early removal of the shuttering to catch up the entire floors, say about 50-60 floors. So it is pertinent to talk a few minutes about post-tensioning and followed by the completed projects of post-tensioning in this country. We will draw your attention for a few minutes. See, our company has done more than 2,000 projects with the support of all the consulting engineers of Hyderabad. And our team were more responsible in doing the projects with the two buildable scores. One is the scoring point stands on the design of the experience, and the next point stands on the system approval. Most of the consultants, they would know how these forces transferred. You need to understand the system approval of any pre-stressing is important, where we need to undergo a stringent test of anchorage efficiency, load transfer and fatigue. If these tests are complied, because these are the standards set by FIB. FIB, they set the standards that these tests are important to comprehensively adopt the system, and that system will be able to transfer the force required. Because the force is approved by the consultant, but it is imperative, it is most important that the forces are transferred. Keeping that into mind, our team who have been in India for last 20 years have accomplished 8,500 projects in this country. Because post-tensioning is last 2 decades only it has become very popular. And second is, we have worked with more than 1,500 structural consultants in India, and we have accomplished 80 crore square feet of post-tension slabs, which is Asia's biggest score ever. A pre-stressing company have reached that score. These are all able to achieve because of the complete understanding and cooperation and support from the structural consultants of this country. In this, I would like to say, and Hyderabad structural consultants are way ahead. In 2000 itself, they have agreed to adopt this technology, and in Hyderabad, more than 85% they have adopted post-tensioning in every viable building, and that is the way forward. And next is, the post-tensioning have to be applied to the tall structures, complying to the codal practice. So we are very responsible in that. And the last is, I would like to thank all the structural consultants who have given us a great chance. Our team, the most experienced team, fortunate our company has in India, who have got more than 25 years of experience in design and as well as execution. That has made us to accomplish 4 lakh metric tons of post-tensioning we have done. In the last years, 4 lakh metric tons of post-tensioning, the only company that has been achieved throughout India. That is again because of the support we have got it. And you will ask, what is 4 lakh metric ton of post-tensioning? 4 lakh metric ton of post-tensioning has replaced 10 lakh metric tons of mild steel. That is the most responsibility the company has taken place, which has enhanced the construction process. So thank you once again to all the consultants, all the developers, all the architects, that this post-tensioning is becoming very popular, and it is going to be more required in future. So next few minutes, I request all of you to draw your kind attention to the slides, which will be really a catching up for all the construction industry participants. These are all the projects of not images, but completed projects in India. Thank you very much. Thank you once again for all the organizers. Thank you.
The entire team. The team of you guys.
8,500 projects would not have happened without this experienced team of designers and execution. So please, I request the audience leaders which completely understood the requirement of the structural consultant working from zone 1 to zone 5. Thank you very much.
Thank you, gentlemen. Now we move on to the next session by Professor Penang. The topic is base isolation of tall buildings, suppression of wind-induced vibration by tuned mass dampers. Welcome, Professor Penang, for the presentation. The presentation time would be 40 minutes and we will have 5 minutes for question and answers. So please keep your questions crisp, and further questions in case there is lack of time will be taken over the email. Thank you. So Professor Penang is currently the Professor of Structural Engineering at the School of Engineering, Asian Institute of Technology. He is a highly accomplished member of the structural engineering industry. He is an accomplished undergraduate studies at University of Thailand, followed by graduate and doctorate in civil engineering from the University of Tokyo. His selected projects are wind tunnel testing of 200 meters, wind tunnel testing of 40 meters high Buddha statue again, wind tunnel testing for structural wind loads, static and dynamic loads for the Rama 8 cable stayed bridge in Bangkok. I think he has many feathers to his cap. So let's enjoy his presentation now. Thank you.
Okay. Good afternoon. I'm just worried that you will have a very late lunch today because of me. Well, engineering at AIT, and many speakers that following after me are also coming from AIT and AIT Solution. So maybe I just use this one slide to explain AIT. And we are focusing on engineering, environmental, and management studies. AIT was founded in 1959, and we have students coming from many different countries. Faculty members are also from many different countries. So it is really an international institution. I think that's a brief, but I think my colleagues may explain more about AIT later. So that is just the introduction about my institution. Also, we are located not very far from Bangkok. It's about 50 kilometers north of Bangkok. So you are all welcome to visit our institute. Next, please. Okay, let me control from here. Okay. Well, the topic assigned to me was seismic-based isolation of tall buildings and suppression of wind-induced vibration of tall buildings by using Joule mass damper. I decided to add a few more topics. Let's start from one topic: suppression of wind-induced vibration in tall buildings by using Joule mass damper. Many tall buildings are quite vulnerable to the vibration problem. They are, dynamic structure. Okay? When you make it tall, they become flexible. And they can be shaken by effect of wind. Sometimes the vibration level is too high, and you need to suppress them. Keep it in an acceptable level. Okay? One example is shown in this slide is Taipei 101, the tallest structure in Taiwan. If you visit Taipei city, you can go to this building, go up to the top floor, and you will find a large pendulum as shown on the right-hand side. Okay, this is a really large pendulum. a pendulum with a mass of around 700 tons, hanging by the pendulum rope with a length of around 11 meters. So this is a large size pendulum, occupy about the space of about 5 floors. You can all see this one. They need this one because this Taipei 101 is quite vulnerable to the effect of windstorm. And you need to keep the vibration induced by wind within acceptable level. If the vibration is too high, it will create a high acceleration level, and it will create motion sickness to the people on the top of the buildings. So this pendulum was installed to suppress the vibration. Okay, the idea is, if you want to make it work, the pendulum need to have a sufficiently large mass. In this case, it's about 700 or 800 ton mass. And you need to tune the vibration frequency of the pendulum with the vibration frequency of the tall building. The vibration of tall building is quite low, 0.1 hertz, 0.2 hertz. You need to have a large size pendulum like this. Not so easy to construct. It looks simple, but you need to have a structure to support this. The mass damper can have many other different forms, not just pendulum. It can be sloshing water damper, as presented by the first speaker, Engineer Martit. Have many other forms, but at AAT we are interested in this particular form. Just a mass supported by rubber bearing, but there are many stages of rubber bearing. The rubber bearing looks like this. Each rubber bearing is not just rubber bearing. It has many steel plates inside. It's called steel laminated rubber bearing. You may have seen this type of bearing supporting bridge and others. So it's kind of a common rubber bearing with steel laminated in short period or low frequency to match with the low frequency building. It also can deform in lateral direction with a large deformability. The size of the June mass damper will occupy only small space. The construction is quite simple. This type of bearing actually can use outdoor, but now we put it indoor, so it's very long life. And the key point is it's low cost. Because this type of bearing are quite available commercially. Now, if you go back and look at Taipei 101, and if I have a chance to redesign the June mass damper, I can put our type, and it will occupy only that space, only a few floors, maybe 1 or 2 floors. And then you will have the space back to you, that you can use it, that the space on the top of the tall building is very expensive. So you can actually make a practical June mass damper, this approach. Okay. This is an actuator in our checking table. And this work is as when he finished his job, then he got a master's degree. Okay, after we have an accurate mathematical model of the June mass damper, then I give assignment to another student, master student. This time is to redesign the June mass damper of this type for a real building. So we can design a damper of around 1,000 tons, more than 1,000 ton size, putting in many stages of rubber bearing, and we design it to be effective on both X and Y direction. Okay. So I hope you can see that. This is the response time history of top floor acceleration. Without Joule mass damper is shown in a gray color. So you have rather high horizontal acceleration above the threshold level that is kind of acceptable level, 15 milli-G horizontal acceleration. So without Joule mass damper, acceleration will be too high. People will have motion sickness. But after we install Joule mass damper, it's reduced to the black color. So that shows the effectiveness of the Joule mass damper. This is only in X direction, but we can check the response in Y direction as well. So you can see that this is a plot of X and Y direction. So you can see kind of a movement trajectory of the top floor. The gray color is the case without Joule mass damper. The green color is the case with Joule mass damper. So you can see the effectiveness in reducing occupy very low space. I think it can be quite practical, and you can apply in many projects in the future if you are involved with this similar problem. Okay, now let me change the subject. Now I change the subject from wind to earthquake. Starting with low-rise building first, we will go to high-rise. Conduct a kind of column jacketing. There will be more sheet. We can have a larger column, and this we can have a larger column, and this is professional technique in strengthen buildings, concrete buildings, to make it stronger against earthquake. Now I want to show that they are not just this and our local universities. So you can see the brace, the black one. It's not just a normal steel brace. It's a bucking restraint brace. Okay? When the building sway to the right, it will create tension in the brace. If the sway amount is high, then it may create yielding in tension in this brace. But when it swings backward to the opposite side, it will create compression load into the truss, into this steel. But if it's a normal steel member, it will be buckle. So in bucking restraint brace, be buckle because it's restrained. So it can yield in compression. Okay, this is a difference between a normal steel brace. So the brace is able to yield in both tension and compression. So it can dissipate a lot of energy. The main function is under compression load. So if you look back and look forward, you can see that it can deform a lot. It can yield in tension, it can yield in compression. So to increase, the brace is not for increasing lateral strength. It is not for increasing lateral stiffness, absorbing vibration energy. So we just put a minimum amount of the brace and it will be okay. In this case, in this building, we just put 4 braces in one direction and 4 braces in another direction. The cost of this modification is quite low. It's around 10% of the building cost. And another thing is, when you put this brace, the load to the foundation is not increasing, but the deformation will be reduced. So you don't have to modify any foundation. So this idea actually is quite practical and is used a lot in Japan within acceptable level. This is another type of retrofitting technique that you may know. This is just carbon fiber reinforced polymer sheet. We just wrap it around the column. Okay, we put the epoxy glue first and wrap it around the column. This is done by a master student. So, and you know, master students have no skill in executing the field work. So if they can do it, then anyone can do it. Okay. You can see here, we fix the base of the column to the floor. And we apply actuator force at the top. We apply vertical load to the column as well in this frame. And we can apply cyclic deformation to this structure back and forth from small amplitude to very large amplitude. Okay, if you compare between the one without carbon fiber reinforced polymer wrapping and the one with wrapping, you can see a completely different behavior. Okay? The one without wrapping, the concrete will crush, concrete will disintegrate. Reinforcement bar will be buckled. It cannot carry vertical load anymore. But when you wrap it, everything will be confined. The bar will not be buckled. The concrete will remain working as a good piece. Okay, I just show you that there are many ways to change the behavior of the structure. Okay, another way to modify the structure is to use the base isolation. Okay, because if you fix the base of the structure to the ground, when the foundation structure, you put something in between. This case is a rubber bearing. Okay. Same type as earlier. It's a kind of steel laminated rubber bearing, but it has to be a thick rubber bearing. And you put the whole building on top of steel laminated rubber bearing. That rubber bearing can carry a large amount of vertical load. Okay, very high load carrying capacity. It has a very high vertical stiffness, but it has extremely low lateral stiffness. Okay, so the structure will be deforming into the lateral direction at the isolation bearing. So I'm going to show you one example how it works. So this is a case study building that the Department of Public Works in Thailand is planning to put the base isolation rubber bearing underneath this building. So I was involved in the project. So I give this problem to one of my master students, Acharapan. I asked her to redesign this building by putting base isolation bearing under each and every column. Okay? So she just modified the foundation system. And I asked her to use only commercially available rubber bearing. So she actually looked into the market and she identified that we need to have 5 different sizes of the rubber bearing because we have a different size of the column. So this is shown here, the location of the rubber bearing with a different color in different size. KV means vertical stiffness. KH means horizontal stiffness of the rubber bearing. And P critical means vertical load carrying capacity of each rubber bearing. So you can see that KV by KH is about 1,000. It means it's very stiff. The vertical stiffness is about 1,000 times of lateral horizontal stiffness. Okay? And the vertical stiffness of the rubber bearing, one rubber bearing is approximately equal to axial stiffness of one column in one floor. So it doesn't change much the property of the structure in vertical direction, but it changes the lateral property of the structure. Okay, now let me show you how it works. This is, to understand how it works, we have to first look at the building without base isolation bearing. So this is a building without base isolation bearing, subject to design basis earthquake ground motion. Okay, you can see this. We conduct a kind of analysis using Perform 3D software of CSI. And you can see the movement of the structure and change in the color. Oh, well, actually, in reality, the structure will not deform this much, but we just magnify it 70 times so that you can see it by your naked eye. And the color show the level of damage. The red means seriously damaged. So with design basis earthquake, the structure is going to have a serious damage in the columns, in the beams, in the brick wall. So you may not be able to use the building after this one, after the earthquake, design basis earthquake. It's going to have an impact to the content inside. It's going to have an impact to the people inside the building as well. Now, this is a modified structure with base isolation. Subject to the same ground motion, we don't change any design of the top of this building. We don't change at all. But we just change the foundation system, putting isolation bearing. And now you can see the different performance. Okay, there will be a large lateral movement at the base isolation layer. There will be less damage. The color remains green or yellow, but not so much red. So they still have some damage to the buildings. But the damage is within something acceptable. And you can use the building after the earthquake. Of course, this modification will increase the cost of the building, but it pays back well. You will have good performance of the structure by this base isolation. Now, this is something maybe many people know already because we apply base isolation to many low-rise and mid-rise buildings. But the idea is this kind of approach can be used also for tall buildings. And this idea is quite popular in Japan. Now I show you, this is the picture of Professor Kazuhiko Kasai, one of my good colleagues, partners. When we visit his lab, he showed the base isolation system of a tall building in Tokyo Tech campus. You can see that they put the rubber bearing underneath the foundation, the structure of tall buildings. This time not low-rise, mid-rise, but this is a very tall building, carry a very high gravity load. They can do that with the normal rubber bearing. Now, but to understand how effective of this system, I think you have to first understand the response of the structure tall building with the fixed base. Well, this is a first vibration mode. The tall building have many vibration modes. This is showing this sway in the first mode. The deflection, the shear force, and overturning moment. You can see how the response vary along the height. When the deflection reach the maximum, you have a maximum shear, you have maximum overturning moment. Okay, this is first mode. When you have the second mode, vibration is vibrate in the different period. In the picture in the middle, you can see the dotted line. It shows the upper bound, maximum shear force. We call this shear force demand. It can be either positive or negative. Okay, and you have maximum overturning moment demand. Okay, so that shows you the maximum level of force produced by earthquake. If this demand exceeds the capacity, then you have the damage, then you have a problem. So we have to keep this demand below our capacity. Now I assigned several students working on this one. I'm thinking about if we put base isolation bearing, this time underneath the tall building, what will happen? Okay, just normal rubber bearing. So you can see here, three pictures. On the left is shear load. The green one is the case when we fix the base to the ground. No. The red one is one when we fix the base to the ground. The green one is when we put isolation bearing. The second picture is about story drift ratio related to the formation in the building, impact to the wall partitions. On the right-hand side is a floor acceleration. This one will show you is an index of how it's impact to the content inside the building. So you can see not just a few 10%, 20% reduction. It's reduced by several by a big factor, okay? You can entirely change the structure of the structural system. You can save a lot of structural materials if you put base isolation bearing underneath this. This is not anymore based on the conventional isolation concept, not just shifting the frequency, but it's actually modifying the dynamic property of the structure. We learned this in detail, but I think this proves how effective it is. Now I come to the last topic that I want to explain. We are talking about structural health monitoring system. When you have a tall building and it's hit by a ground-shaking earthquake, people may be panicked. People may feel worried about their structure. The building owner may call you in the middle of the night to come and inspect their building, asking whether it is safe to come back and use the building or not, whether they have any major damage inside your structure or not. Okay, that will require some investigation effort to do that. But if you put some vibration sensor into that, I think you can improve, you can rapidly identify possible damage inside the building. Okay, this is a simple acceleration sensor. It's again commercially available. It's available, it's commonly used, and we can put it not every floor, but just on some specific floor, on the top, on the middle, at the base. Then we can identify if we have a proper procedure. In a traditional approach, we review many literature, and we found that the most common approach that people use is to use this acceleration sensor and identify the dynamic property of the structure, natural frequency, vibration mode shape, damping ratio of the structure. These are basic ones. And once it's hit by earthquake, they will again check natural frequency, mode shape, damping ratio, and see whether they have some change or not. So the change will indicate some damage inside the structure. In our approach, we think this traditional approach is not effective at all. So we use a completely different approach. We actually convert the signal, and we know that it's a sum of 3-4 vibration modes. And so we try to separate them into mode 1, mode 2, mode 3. Each mode we try to find the modal coordinate or the amplitude of response of each mode. So once you know the response of each mode, then you can estimate not just acceleration, you can estimate lateral deflection, you can estimate story drift, you can estimate the floor acceleration, you can estimate bending moment in the column, you can estimate shear in the shear wall. You can get all the response you want, and you can compare with the capacity. Okay, that is the idea. So I skip some because the time is almost limit. So the idea is we have been working out theoretically how to separate the response that have a many mode mixed together. We can separate them into response of mode 1, mode 2, mode 3, or any other modes that are important by the technique called orthogonal filter. And then we estimate how much will be the best shear in that building. Okay? The red one is our estimate by using only acceleration response. The black one is the correct answer. So it seems that we can estimate shear quite accurately using only acceleration response. And we are doing that also along the height of the building, because we are not only interested in the base shear, we're interested in the overturning moment along the height, interstory drift along the height. So our estimate shown in red color is matching well with the actual response in the black color. But all these that I show you are based on numerical analysis using software, finite element model. So it's not real yet. So I give assignment to another master student to try to test that concept. So this time we put accelerometer into very simple structure at different locations. You can see the red dot. And at the same time, we put the strain gauge to the column to check the bending strain and shear strain, the shear force and bending moment at 2-3 locations in the structure. And we're trying to use acceleration data to estimate shear force or shear strain, bending strain at the location. So we have strain at some mid-height and strain at the base to estimate that. So this shows you how it works. We produce checking force, check the structure vibrate, and we actually obtain different response. You see in the mid picture is show the acceleration response, and then we use the green one to estimate the bending strain in the column. And it's matched well with the estimate, the actual measured strain. So I show you this example. The red one is the bending moment, bending strain and shear strain estimate from, the estimate is a black one. It's an estimate from acceleration data. And the red one is from the direct measurement. So it means that you don't have to put many different types of sensor, just the acceleration sensor. And you can obtain all type of response you want to know by this proper conversion. So based on this, we are actually putting, I'm about to finish now. Yeah, this is an actual sensor. You know, we put 10 of them inside the real building. And the sensor size is quite small, and we put it on the ceiling. So no one will disturb it. And we connect it with the battery and the power supply. It's very, very simple. You know, one unit of acceleration sensor have 3 axes of accelerometer. In the past, it used to cost you about $5,000 per unit. Today, it costs you $500 US. So it is much easier. Oh, okay. Okay, and after we put the sensor, we then use many students, engineering students, to check the building. We can, instruct them to check the first mode, X, first mode, Y, first torsional mode, second mode in X, second mode in Y. All that can be done by just changing the frequency. And the result looks very promising. So we are still working on this project. If you are interested, we can share this idea. It can be applied to many other structures, and the cost is quite low. And I think you, as an engineer, you will see, you will learn more about the structure that you have constructed by yourself. I think that's all for my presentation. You will come back and see me again tomorrow morning. I will present about wind tunnel model test. Thank you very much for your good attention. Sorry.
Thank you so much, Professor, for that wonderful, wonderful presentation. And I think we are really running out of time, so we'll take 2 quick questions and maybe rest during the lunch time.
Sir, what is the life of the rubber in bearing? And if we want to retrofit a building, how to induce this or how to introduce this bearing concept?
I'm not
what
catching.
What is the life of the rubber in the bearing?
Life
of the rubber. What you use? You said the bearing is.
Durability of what?
Yeah, durability of the rubber.
I actually present many things. The life, the June mass damper or buckling resistant brace or
no
base isolation. Oh,
yes.
okay, base isolation. You know, they use a commercially available rubber bearing with steel laminated plate. This has been used outdoor as a support for bridge girder, and it still functions well even after 20, 30 years. It's subject to direct sunlight, rainwater, oxygen in the air, so it works well. But now in our application, we put it inside the building. It's going to last longer. And even if there is a problem, you can easily replace them. Okay? It's a big problem anymore.
If we want to retrofit a building by introducing this bearing, how can we do it?
You mean base isolation?
Yeah.
I think if you already have existing tall building, it will be extremely difficult. But if you are designing a new one, and you design from the beginning, having this base isolation, it will help you change the design of entire structure. Okay, in the first design stage. Okay, please consider this as option. This will give you another option, especially when you are in high seismic zone.
Thank you, sir.
Yeah. Sir, firstly, a very nice presentation. Thanks for the very nice presentation, sir. Myself, Krishnagant. I have one query, sir, regarding this pendulum type of dampers, whatever you have used in that type 101, that explanation in the initial stage of presentation.
Yeah. Actually, we try to promote
yes.
different type of damper.
Yeah, for that case, it is dedicated space is required for like around 10 floors. So, do you have any substitute to that dampers?
Substitute?
Means like any other way, means here we are using so much space in the building.
Oh, okay. For tall buildings,
yes.
You want to reduce the vibration.
Yes.
You have many possible options. You can use buckling resistant brace installed in some floor. You can use viscose damper. You can use this type of June master on the top of the thing. There are many possible options. So what to do is to check, and you may choose the one that you like most. So each of these have advantage and drawbacks. So I just want to show you that if you choose dynamic June mass damper, then this configuration will probably be the most practical one.
Okay, thank you.
Sir, I'm Santosh here. I'm mostly working on the retrofitting of the buildings. So I have a question here. When you are shown a CFRP strengthening system, so I'm here. Onto your left side corner.
Oh, okay, I see you now.
Yeah. So you are shown a CFRP wrapping system.
Okay.
So in that, have you done the end anchorage edges also, or it's only a wrapping to the column you have done? Because I have with the garages when I'm doing a CFR strengthening.
I cannot catch your question well, but you can apply CFRP. The most effective will be the round column.
Yeah,
but we find for rectangular column, if you inclinate the sharp corner a little bit, a bit around that, it's still quite effective. The example I show is a rectangular shape column.
So my question is, wrapping is very easy, but how do you connect it to the foundation?
No, you don't have to connect to the foundation. You just wrap it around the part that you expect it to have damage. Okay? So for example, for the column, you may have high bending moment on the top and at the base for each floor of the column. So you wrap it around so.
But that moment we need to transfer the foundation also, sir.
Actually, CFRP wrapping is to modify the performance after the yielding of the column. Okay? So after yielding, the shear load will not increase anymore, but it will improve the formation ability of the column. We call ductility. So the shear transfer to the lower floor, to the foundation will not be increased. So you don't have to modify the foundation.
Okay.
Sir, yeah, I have one question.
Okay.
It's a very interesting presentation just before the lunch. The question is, while considering the base isolation technique, so did you consider both earthquake and wind effect, or only is for earthquake?
Base isolation is for
but
only. Yeah, not for wind.
Okay, but if we consider it combined effects, the results may vary because of downward effects of wind, also interference effects.
I can't. Sorry, I cannot hear you well.
Okay.
So sorry, I cannot hear you well. So I'm trying to understand the question.
I'm just asking, like, if we consider both wind and earthquake effects,
I think you may need different measure for different type of excitation.
Yeah.
For wind, you may modify the geometry of the structure. You may modify some other aspect of the structure.
Yeah.
But for earthquake, base isolation is one way, and it's quite effective for that. But when you put base isolation to improve the performance of building against earthquake, it will also affect the performance against wind. So you need to check that as well. But I think it's still working well.
Okay, yeah. Combined effects may give different results. That's what I was asking. Maybe the surrounding wind environment that can.
I just want to add one more thing, that if your structure have podium, it will make even more effective when you put a base isolation. Okay.
I have a small query. First of all, thanks for such wonderful presentation, sir. Myself, Srikar Ramod, and so I'd like to know what is the metal index specification of this mass damper, and what is the lifespan of this thing?
The durable is
What's the lifespan
the mass
and
ratio.
metal specification?
Basically, to make a Joule mass damper work, the Joule mass damper must have some reasonable mass size. So approximately, you need roughly about 0.5% of the building mass. Okay? So you have to estimate the total mass of your building. Make sure that your size of your Joule mass damper will not be smaller than 0.5%. And that can turn into 1,000 tons of mass. Can be a big pendulum, can be a big mass, as I shown you in the picture.
So this lifespan will continue till the lifespan of the structure?
The lifespan, well, will be inside the building, so you can keep checking the performance. And all the components in the Joule mass damper can be easily replaced. So, and as I explained, use a rubber bearing. The service life will be quite long.
Yeah. So thank you so much. We will take the question later, please. And you can connect during the lunch time, or you can write back the questions on a mail. So thank you so much, Professor Panang, to join us here. And I will request Advisor C.A. Prasad Garu and Vice President South, Sandeep Shirketkarji, to please kindly felicitate Professor Panang. Sandeep Shirketkarji, B West. We make 230. If we make it 230, at least the 245 people will come. 240? The number of questions vis-a-vis the applause seems to be very less. It should be proportional. So thank you so much, ladies and gentlemen. We break for lunch now. So it's 2 o'clock now, so we join back at 2:40. Let's not be late, and let's come back on time. Enjoy your lunch.